Andrew Wiles' proof of Fermat's last theorem is a proof of the modularity theorem for semistable elliptic curves released by Andrew Wiles, which, together with Ribet's theorem, provides a proof for Fermat's last theorem. Both Fermat's last theorem and the modularity theorem were almost universally considered inaccessible to proof by contemporaneous mathematicians, seen as virtually impossible to prove using current knowledge. Wiles first announced his proof on Wednesday, 23 June 1993 at a lecture in Cambridge entitled Elliptic Curves and Galois Representations. However, the proof was found to contain an error in September 1993. 1 year later, on Monday 19 September 1994, in what he would call the most important moment of his working life, Wiles stumbled upon a revelation so indescribably beautiful, so simple and so elegant, that allowed him to correct the proof to the satisfaction of the mathematical community. The correct proof was published in May 1995. The proof uses many techniques from algebraic geometry and number theory, and has many ramifications in these branches of mathematics. It also uses standard constructions of modern algebraic geometry, such as the category of schemes and Iwasawa theory, and other 20th-century techniques not available to Fermat. The proof itself is over 150 pages long and consumed 7 years of Wiles' research time. John Cote described the proof as one of the highest achievements of number theory, and John Conway called it the proof of the century. For solving Fermat's last theorem, he was knighted, and received other honors. Progress of the previous decades. Fermat's last theorem states that no three positive integers a, b, and c can satisfy the equation if n is an integer greater than 2. In the 1950s and 1960s, the modularity theorem, a connection between elliptic curves and modular forms, was conjectured by the Japanese mathematician Goro Shimura based on ideas posed by Yutaka Taniyama. In the West it became well known through a 1967 paper by Andrew Wiles, who gave conceptual evidence for it. Thus, it is sometimes called the Taniyama-Shimura-Wiles conjecture or the Taniyama-Shimura conjecture. It states that every rational elliptic curve is modular. On a separate branch of development, in the late 1960s, Yves Hellegouarch came up with the idea of associating solutions of Fermat's equation with a completely different mathematical object, an elliptic curve. The curve consists of all points in the plane whose coordinates satisfy the relation. Such an elliptic curve would enjoy very special properties, which are due to the appearance of high powers of integers in its equation and the fact that n plus bn equals cn is an nth power as well. In 1982 to 1985, Gerhard Frey called attention to the unusual properties of the same curve as Hellegouarch, now called the Frey curve. This provided a bridge between Fermat and Taniyama by showing that a counterexample to Fermat's last theorem would create such a curve that would not be modular. Again, the conjecture says that each elliptic curve with rational coefficients can be constructed in an entirely different way, not by giving its equation but by using modular functions to parametrize coordinates x and y of the points on it. Thus, according to the conjecture, any elliptic curve over Q would have to be a modular elliptic curve. Yet if a solution to Fermat's equation with non-zero a, b, c and n greater than 2 existed, the corresponding curve would not be modular, resulting in a contradiction. As such, a proof or disproof of either of Fermat's last theorem or the modularity theorem would simultaneously prove or disprove the other. In 1985, Jean-Pierre Serre proposed that a Frey curve could not be modular and provided a partial proof of this. This showed that a proof of the semistable case of the modularity theorem would imply Fermat's last theorem. Serre did not provide a complete proof of his proposal. The missing part became known as the epsilon conjecture or epsilon conjecture. Serre's main interest was in an even more ambitious conjecture, Serre's conjecture on modular Galois representations. which would imply the modularity theorem. Although in the preceding 20 or 30 years much evidence had been accumulated to form conjectures about elliptic curves, the main reason to believe that these various conjectures were true lay not in the numerical confirmations, but in a remarkably coherent and attractive mathematical picture that they presented. Equally, it could happen that one or more of these conjectures were actually untrue. Following this strategy, a proof of Fermat's last theorem required two steps. First, it was necessary to show that Free's intuition was correct, that the above elliptic curve, if it exists, is always non-modular. Frey did not quite succeed in proving this rigorously. The missing piece was noticed by Jean-Pierre Serre and proved in 1986 by Ken Ribet. Second, it was necessary to prove the modularity theorem, or at least to prove it for the subclass of cases which included Free's equation. Ribet's theorem, if proved, would show that any solution to Fermat's equation could be used to generate a semi-stable elliptic curve that was not modular. The modularity theorem, if proved for Free's equation, would show that all such elliptic curves must be modular. The contradiction implies that no solutions can exist to Fermat's equation, thus proving Fermat's last theorem. In the summer of 1986, Ken Ribet succeeded in proving the epsilon conjecture. He demonstrated that, just as Frey had anticipated, a special case of the modularity theorem, together with the now proved epsilon conjecture, implies Fermat's last theorem. Thus, if the modularity theorem is true for semi-stable elliptic curves, then Fermat's last theorem would be true. However, this theoretical approach was widely considered unattainable, since the modularity theorem was itself widely seen as completely inaccessible to proof with current knowledge. For example, Wiles' ex-supervisor John Coates states that it seemed impossible to actually prove, and Ken Ribet considered himself one of the vast majority of people who believed it was completely inaccessible. Hearing of the 1986 proof of the epsilon conjecture, Wiles decided to begin working exclusively towards a proof of the modularity theorem. Ribet later commented that Andrew Wiles was probably one of the few people on Earth who had the audacity to dream that you can actually go and prove it. Wiles' proof. Overview. Wiles opted to attempt to match elliptic curves to counted modular forms. He found that this direct approach was not working, so he transformed the problem by instead matching the Galois representations of the elliptic curves to modular forms. Wiles denotes this matching that, more specifically, is a ring homomorphism. R is a deformation ring and T is a Heck ring. Wiles had the insight that in many cases this ring homomorphism could be a ring isomorphism. He realized that the map between R and T is an isomorphism if and only if two abelian groups occurring in the theory are finite and have the same cardinality. This is sometimes referred to as the numerical criterion. Given this result, Fermat's last theorem is reduced to the statement that two groups have the same order. Much of the text of the proof leads into topics and theorems related to ring theory and commutation theory. Wiles' goal was to verify that the map RT is an isomorphism and ultimately that R equals T. In treating deformations, Wiles defined four cases, with the flat deformation case requiring more effort to prove and treated in a separate article in the same volume entitled Ring Theoretic Properties of Certain Heck Algebras. Gerd Faltings, in his bulletin, on p. 745, gives commutative diagram, or ultimately that R equals T, indicating a complete intersection. Since Wiles could not show that R equals T directly, he did so through Z3, F3 and T per meter via lifts. In order to perform this matching, Wiles had to create a class number formula. He first attempted to use horizontal Iwasawa theory, but that part of his work had an unresolved issue such that he could not create a CNF. At the end of the summer of 1991, he learned about a paper by Matthias Flach, using ideas of Victor Kolyvagin to create a CNF, and so Wiles set to his Iwasawa work aside. Wiles extended Flach's work in order to create a CNF. By the spring of 1993, his work had covered all but a few families of elliptic curves. In early 1993, Wiles reviewed his argument beforehand with a Princeton colleague, Nick Hatz. His proof involved extending approaches which had recently been developed by Kolyvagin and Flach, which he adopted after the Iwasawa method failed. In May 1993, while reading a paper by Mazur, Wiles had the insight that the 3/5 switch would resolve the final issues and would then cover all elliptic curves. General approach and strategy. Given an elliptic curve E over the field Q of rational numbers, for every prime power, there exists a homomorphism from the absolute Galois group to the group of invertible 2x2 matrices whose entries are integers representation for some L and N, and from that to the modular form. In the case L equals 3 and N equals 1, results of the Langland tunnel theorem show that the representation of any elliptic curve over Q comes from a modular form. The basic strategy is to use induction on N to show that this is true for L equals 3 and any N. That ultimately there is a single modular form that works for all N. To do this, one uses a counting argument, comparing the number of ways in which one can lift A and the number of ways in which one can lift a representation has an image which is too small. One runs into trouble with the lifting argument, and in this case, there is a final trick, which has since taken on a life of its own with the subsequent work on the Serre modularity conjecture. The idea involves the interplay between the and representations. See Chapter 5 of the Wiles paper for this 3/5 switch. Structure of Wiles' proof. In his 108-page article published in 1995, Wiles divides the subject matter up into the following chapters. Introduction 443 Chapter 1 455 1. Deformations of Galois representations 472 2. Some computations of cohomology groups 475 3. Some results on subgroups GL2 Chapter 2 479 1. The Gorenstein property 489 2. Congruences between Heck rings 503 3. The main conjectures Chapter 3517 Estimates for the Selma group Chapter 4 525 1. The ordinary CN case 533 2. Calculation of eta Chapter 5541 Application to elliptic curves Appendix 545 Gorenstein rings, and local complete intersections Gerd faultings. Subsequently provided some simplifications to the 1995 proof, primarily in switch from geometric constructions to rather simpler algebraic ones. The book of the Cornell Conference also contained simplifications to the original proof. Reading and notation guide. Wiles' paper is over 100 pages long and often uses the specialized symbols and notations of group theory, algebraic geometry, commutative algebra, and Galois theory. One might want to first read an email Ken Ribet sent in 1993, Hesse links quick review of top-level issues, which gives just the elementary algebra and avoids abstract algebra, or Danny's webpage, which provides a set of his own notes and lists the current books available on the subject. Weston attempts to provide a handy map of some of the relationships between the subjects. FQ. Gu provides an award-winning review of some of the required topics. Faulting's 5-page technical bulletin on the matter is a quick and technical review of the proof for the non-specialist. For those in search of a commercially available book to guide them, he recommended that those familiar with abstract algebra read Heligu Arch. Then read the Cornell book, which is claimed to be accessible to a graduate student in number theory. Note that not even the Cornell book can cover the entirety of the Wiles proof. The work of almost every mathematician who helped to lay the groundwork for Wiles did so in specialized ways, often creating new specialized concepts and yet more new jargon. Subscripts and superscripts are used extensively in the equations because of the numbers of concepts that Wiles is sometimes dealing with in an equation. See the glossaries listed in List of Mathematics Topics #Pure Mathematics, such as Glossary of Arithmetic and Diophantine Geometry. Daney provides a proof-specific glossary. See Table of Mathematical Symbols and Table of Logic Symbols. For the deformation theory, Wiles defines restrictions on the deformations as Selmer, ordinary, strict or flat, and he uses the abbreviations list here. He usually uses these as a subscript, but he occasionally uses them as a superscript. There is also a fifth case, the implied, unrestricted case, but note that the superscript UNR is not an abbreviation for unrestricted. QUNR is the unramified extension of Q. A related but more specialized topic used is crystalline cohomology. See also Galois cohomology. Some relevant named concepts: Hasse-Weil zeta function, Mordell-Weil theorem, Deligne-Serre theorem, grab bag of jargon mentioned in paper, cover and lift, finite field, isomorphism, surjective function, decomposition group, J invariant of elliptic curves, abelian group, Grossen character, L function, abelian variety, Jacobian, N model, Gorenstein ring, torsion subgroup, congruence subgroup, eigenform, character, irreducibility, image, dihedral, conductor, lattice, cyclotomic field, cyclotomic character, splitting of prime ideals in Galois extensions, quotient space, quotient group, announcement and subsequent developments. Wiles' proof was initially presented in 1993. It was finally accepted as correct, and published, in 1995, because of an error in one piece of his initial paper. His work was extended to a full proof of the modularity theorem over the following 6 years by others, who built on Wiles' work. Announcement and final proof. During 21 to 23 June 1993, Wiles announced and presented his proof of the Taniyama-Shimura conjecture for semi-stable elliptic curves, and hence of Fermat's last theorem, over the course of 3 lectures delivered at the Isaac Newton Institute for Mathematical Sciences in Cambridge, England. There was a relatively large amount of press coverage afterwards. After the announcement, Katz was appointed as one of the referees to review Wiles' manuscript. In the course of his review, he asked Wiles a series of clarifying questions that led Wiles to recognize that the proof contained a gap. There was an error in one critical portion of the proof which gave a bound for the order of a particular group. The Euler system used to extend Flach's method was incomplete. The error would not have rendered his work worthless. Each part of Wiles' work was highly significant and innovative by itself, as were the many developments and techniques he had created in the course of his work, and only one part was affected. Without this part proved, however, there was no actual proof of Fermat's last theorem. Wiles and his former student Richard Taylor spent almost a year resolving this issue. Wiles indicates that on the morning of the 19th of September 1994 he realized that the specific reason why the Flach approach would not work directly suggested a new approach based on his previous attempts using Iwasawa theory, which resolved the issue and resulted in a CNF that was valid for all of the required cases. On the 6th of October, Wiles asked 3 colleagues to review his new proof, and on the 24th of October 1994, Wiles submitted 2 manuscripts, Modular Elliptic Curves and Fermat's Last Theorem, and Ring Theoretic Properties of Certain Heck Algebras, the second of which Wiles had written with Taylor and proved that certain conditions were met which were needed to justify the corrected step in the main paper. The 2 papers were vetted and finally published as the entirety of the May 1995 issue of the Annals of Mathematics. The new proof was widely analyzed, and became accepted as likely correct in its major components. These papers established the modularity theorem for semi-stable elliptic curves, the last step in proving Fermat's last theorem, 358 years after it was conjectured. popular accessibility. Fermat himself famously claimed to have discovered a truly marvelous proof of this, which this margin is too narrow to contain, but Wiles's proof is very complex, and incorporates the work of so many other specialists that it was suggested in 1994 that only a small number of people were capable of fully understanding at that time all the details of what he had done. The number is likely much larger now with the 10-day conference and book organized by Cornell et al., which has done much to make the full range of required topics accessible to graduate students in number theory. In 1998, the full modularity theorem was proved by Christoph Breuer, Brian Conrad, Fred Diamond, and Richard Taylor using many of the methods that Andrew Wiles used in his papers published in 1995. A computer science challenge given in 2005 is formalize and verify by computer a proof of Fermat's last theorem, as proved by A.